Dank u wel, meneer de decaan. Geachte genodigden, beste collega's, beste Peter. Aangezien er een aantal mensen aanwezig zijn die Engelstalig zijn, stel ik voor dat ik de laudatio in het Engels geef. So, every year the Faculty of Engineering Science appoints an honorary professor, which is an acknowledgement for a non-academic researcher with academic potential. This year, and upon nomination of the Department of Electrical Engineering, also called ISAT, this honor falls to Peter Vetter, who is president of Bell Labs Core Research at Nokia. Now, for those who are not familiar with it, Nokia Bell Labs is an industrial research and development organization with worldwide operations, including today also in Antwerp. Originating from the Bell Telephone Laboratories founded in 1925, it is currently owned by the Finnish company Nokia. Today it consists of two divisions, Core Research and Solutions Research. And the goal of the Nokia Bell Labs is to develop paradigm-shifting ideas that transform the future of humanity and technology. For the last 9 decades, its researchers have been involved in many critical technological breakthroughs. Some examples of important inventions and developments include, for instance, the invention of the transistor in 1947, 75 years ago. The invention of the laser, the invention of the photodiode, of the photovoltaic cell, the basics of information theory with Shannon's law, the first hearing aid for those who need it, the Unix operating system, the languages C, C++, and many others. So no surprise that Bell Labs is often called the idea factory. On the other hand, today we are all using our phones, our laptops, our microphones wirelessly. Being part of Nokia, it is no surprise that large part of the research activities of these Bell Labs today incorporate wireless mobile communications. And the focus is on networks of the future beyond the commercial solutions which are currently installed and are being installed worldwide. This next mobile generation, which is called 6G, promises not only to be faster, but also to support extra applications beyond what we have today, such as virtual and augmented reality, pervasive intelligence, and future generations of Internet of Things. 6G will not only build on existing technologies, it will radically transform what a network can do, fusing the human world, the physical world, and the digital world. What that means, we will hear in the New Year's presentation from Peter Vetter in a few minutes. Now, as president of Nokia Bell Labs Core Research, Peter Vetter leads a team of researchers responsible for the long-term global research of Nokia's core technologies around network architectures, network systems and security, optical systems, and radio platforms. The team is developing innovations to prepare Nokia's core business for the 6G era. His strategy is the combination of fundamental, foundational research, also through collaborations with distinguished academic groups, such as several groups at ESAT, but not exclusively, of course, and solving problems with real industry impact. So this wide span between fundamental research on the one hand and impact on industry and society on the other hand is very representative for the field of engineering science, for which this faculty stands. His team has demonstrated as first and brought to practice several novel communication systems over the years. Personally, he has been awarded as Bell Labs Fellow and Fellow of IEEE for that. For all these reasons, Peter Vetter is nominated as honorary professor of the Faculty of Engineering Science. But before officially inferring this title upon him, we give him the opportunity to personally explain his activities as leader of this research team on the journey towards 6G.
Dankjewel George, dankjewel Peter, dankjewel aan heel de faculteit. Het is een hele grote eer natuurlijk. It's really an honor to receive this. And this is not so much for me as a person, but really for Bell Labs and what it stands for. So a big thank you also to my colleagues, and some of them are here in the room, but actually also worldwide. And a thank you to my leadership team. Actually, incidentally, 2 months ago, we had an off-site leadership team meeting, and yeah, being from Belgium, I kind of organized it here in Belgium. And part of that face-to-face meeting, we used to visit the faculty here. And the lab leaders, each an authority in their field, they said this was really an inspiring visit. They were really energized by the visit. So it really, there is a good vibrance between KU Leuven, one of our distinguished academic partners, and Nokia Bell Labs. In accepting, when we had the first phone call, Peter, you will remember, it said, it's not only an honor, I also felt it was a strengthening and a support. In Dutch, a steun in de rug. Having that honorary professor, it actually symbolizes what I stand for and what I want to drive as research culture in Bell Labs. It is that foundational coupling that also, George, you alluded to, between the foundations of the science and technology innovations. And having that title actually strengthens me. Look, this is what Bell Labs stands for. This is what I stand for as co-president of Bell Labs Core Research. I use the word co-president as an anecdote. We have actually a tandem dual leadership of Bell Labs. My co-president, Thierry Klein, is actually incidentally from Luxembourg. So it's interesting that this industry lab is led by 2 people from the same small countries of this region. But back to the point, really that coupling of scientific research and innovation strengthens me, and I have the support from the CEO of the company, Nokia, Pekka Lundberg, and also my direct managers, the CTO, Nishant Batra. They have the patience and support the long-term investments. We have to take long-term bets, and they will not see the return on investment in the next 3 to 5 years. They trust that for technology leadership, we will deliver with innovations that have a 10 to 20-year horizon. And that is pretty unique for an industry lab. Now, and I want to make that point a bit more, yeah, I think we have the presentation a bit in a wrong at the end already. Let's see if we can fix that. No? Okay, so flip through a few. So I want to illustrate that point a bit more clear. George, you already said the transistor invented 75 years ago. Just a few weeks ago, December 16th was actually the day. And you can really argue, what is the most transformative invention in humanity? And many people will say Maybe it was fire, maybe it was the wheel. I would argue it is the transistor. I mean, just think of it. You have 1 billion transistors just in your handset. The way we communicate, the way we have applications around it, it completely transformed our society. And the reason why I bring this up, yeah, there's the 75th birthday. This was just a few weeks ago. But we should reflect also on what led to this innovation, which way of thinking. And there are 5 points. I have 5 fingers, so there can't be more than 5 points. Point 1, it is go after a real-world problem. Josh already mentioned that as well. Don't go after a problem that is already solved. Yes, you will get a nice research paper somewhere in a conference, but you will not have the impact. So what was the problem that they were solving? Amplifiers. The state of the art for transmission lines and repeaters, amplifiers were vacuum tubes. And also in the radio you have amplifiers. People of my generation, you will remember the Lampenradio. I mean, these vacuum tubes, they were fragile, limited lifetime, consumed a lot of energy, bulky. So they went after a real-world problem to solve that. Second, go after it in a non-evolutionary way. Think out of the box. They didn't go for new filaments and a new structure of anode, cathode, and grid. They went for solid-state physics. Think out of the box. Second ingredient. Third ingredients go really to the fundamentals. They invented a new field of physics, semiconductor physics, and really went into the understanding of how these things work. And then fourth element, multidisciplinary research. The guy at the top left is John Bardeen. He was a theoretician. And the story is that he didn't have an office. They didn't have an office for him. So they put him in the lab together with Walter Brattain on the right-hand side. Walter Brattain was an experimentalist, an engineer with golden hands. And it was that fusion of the two working together that led to these breakthroughs. And then, of course, a very smart department leader, Shockley, that you see sitting and peering to the microscope. But multidisciplinary also in the broader sense. You had material scientists at Bell Labs, metallurgists that really made new semiconductor materials with high purity, germanium, silicon. Very low purity level. High purity level, very low impurity levels. And it leads to my second point that I want to make. They even controlled the level of impurities to control the material properties, N material, P material. So again, the multidisciplinary and embracing that. And then the fifth element is think of your solution and broader applicability. It's not just the amplifier. Once you have an amplifier in a feed-forward, you can create oscillators for radio, for instance. You could use it as a switch. It led to logic devices, integrated processors. They discovered that it was light sensitive and that you could harvest energy. Josh, you mentioned the solar transistor, that you have semiconductors that you control band gaps and that you can use for lasers and tune the wavelength leading. So broad applicability. So in summary, 5 ingredients for successful research that not only apply to the transistor, but to many other inventions, as Georges mentioned, for instance, optical communication, information theory, understanding the limits of information theory, then computer science, Unix, C++. And it is still very much the DNA and the culture of the way we work today. Real-world problem, going after it in a non-evolutionary way, out of the box, really leveraging the scientific insights and the fundamentals, embracing a multidisciplinary approach, and 5, broadening the applicability and see the more general applicability. So I wanted to make that point because it strengthens me in this way of thinking and what Bell Labs stands for. So thanks again for the honorary professorship and helping me in my role, actually. And now to the the topic that was really announced for the lecture here today, the journey then to the future, 6G. So every 10 years we have a new generation of networks. We look to the network of 2030 and beyond, so 10 to 20 years out. But still, 1947 was not only the transistor, it was also the invention of cellular networks at Bell Labs. This memo went around to 20 people in CC, and there was no email, it were real carbon copies that went around, describing a solution to provide a service to any equipped vehicle in the nation. And the way to do this was to reuse spectral bands in small regions, basically inventing the cells. Now, it took many more years before we then really got the mobile telephony, and the real mobile phone was invented by this guy, Marty Cooper. Marty Cooper, in all fairness, was not from Bell Labs, he was from Motorola. And Bell Labs was on the track of any equipped vehicle. Marty Cooper proved that with this brick that he has in his hand, that it could be done really a handset. The project was called the phone in a shoe. And so that in those days, there was a TV series, Maxwell Smart, and that was the inspiration. Right? Now, that thing, 3 kilograms, 10 hours charge time, 30 minutes peak time, he was realistic to say it's not practicable, but it can be done. And we had him for dinner a few years ago, and he explained how his very first phone call was to Bell Labs, to his competitor. And then he said, got you. Well, he said it in a more polite way. But Bell Labs did play an important role in then the further commercial rollout, the Bell systems, to get to the analog first telephone services. And if you remember, the quality was not that good, these analog phones. It was also horrendously expensive. I remember at the time you could be at a crossing and all of a sudden you had people picking up phone in their car. And when you counted the number of people, they say, there's not enough spectrum for all these. Some of them were faking. The phone in those days, the mobile phone, was a status symbol. Now the democratization happened with this. I don't know why this one now switched by itself, but yeah, was the GSM, the digital phone. That's when the large-scale deployment of mobile telephony happened. That was the start of the Nokia success story, also the first GSM call by Nokia and the handsets that were a worldwide success with the 40% market share. Hey, there's an automatic thing that seems to be going on here. Anyways, so I'll try to control that a bit. So since then, our industry has rolled out a new generation of network every 10 years. And every generation went for higher capacity with new radios, with higher frequencies and wider bands. And every generation also went after new applications, as these iconic pictures show you. Every generation is also defined by new platforms, new compute platforms from the mainframe, IBM, and VAX computers to what we have today, the distributed cloud computing. And also new network technologies, going from analog to digital, to circuit-based ATM, to packet-based Ethernet and IP, and then to cloud-based networks, network function virtualization, software-defined networking. And then making those same generations happen also for fixed networks. Also the wireline followed very similar technology evolution, and also the bandwidth is actually very similar, and that's not a surprise because the underlying technology, the silicon technology that enabled the signal processing, was followed the same compute power and generations. And a call out here for the excellent collaboration with Professor Mark Molen and our research center in Antwerp, where we worked on DSL signal processing and vectoring, crosstalk cancellation. That really was important for the leadership of the company in DSL, market leadership and technology leadership. So every generation, new platform, new technology, and also a new defining applications that sets the direction for the research. And there's then also the unexpected applications, famously the GSM with the unexpected SMS text messaging as an example. During the reception, if you have an idea what the unexpected application is for 5G, I'm really interested to hear. But looking now to the future 6G. So what will be the defining technology? What will be the defining platform? And what will be the defining, this is really a bit annoying, but okay, let's try to manage that. The defining application. So the defining technology, if there is a pause button, that would be actually a good idea. Okay, the defining new technology is, you could argue, even higher frequency bands. Shall we go in 5G's millimeter wave? Shall we go to sub-terahertz? Now, you see the question marks, a bit a word of caution, because even the millimeter wave in 5G doesn't really pan out. So, word of caution. The compute platform seems to be a clear direction. AI, using AI in new ways to deal with the complexity of and the automation of networks, and also in new ways maybe at the air interface. And then new applications, the fusion of digital and physical worlds. So let me explain that fusion of physical and digital worlds a bit more, and why that is so interesting and important. So 5G, what 5G is doing well is the coupling between humans and machines, and enabling the industrial Internet of Things. What 6G, what we expect there is a coupling of all our physical world, our human state, our human worlds, synchronously with digital twin models in the digital world. This is enabled by massive scale deployment of sensors and massive scale deployment of AI that enables us to understand what these sensors are sensing. And so with these actual models, digital twin models, in real time, what can we do with that? Well, on one hand, you can transport these models to a different location. You can recreate a model of ourselves and have a holographic representation, recreate our environment, and we interact with each other as if we were there. We can design and co-design 3D models. We can transport those to the location where it wants and 3D print it. Digital twin models also help us understand better possible outcomes, optimize industrial processes. Already today, we have digital twins of machines, for example, jet engines. Understand the state, understand the need for maintenance, anticipate possible failures, and then before they're needed, act on them. Now, it's already happening in 5G. We see this happening at a much larger scale in 6G industrial processes, even at smart city level. And we've been pursuing this vision already for many years. In the meantime, metaverse happened. In 2022, metaverse, and the company Facebook changed its name to Meta. The stock market at the moment isn't sure whether that was the right move, but it became a well-known industry thing. And it basically goes after that same vision that at Bell Labs we've been pursuing already for so many years, the fusion of digital and physical worlds, and then its ability to augment our human existence. Meta, and the way we talk about it today in the larger community is a lot about the consumer metaverse. The social interactions, the gimmicky avatars, the 3D goggle experience. We think of this broader, as I already explained, as the enterprise metaverse, co-design, having efficient interactions in companies, and then the metaverse of the industrial metaverse, really to optimize industrial processes and productivity. Now, to make this happen at a large scale, massive interconnectivity of sensors, actuators, AI engines and AI models, to deploy this in a flexible way, to create new applications in a flexible way, like we create applications today on the cloud, and deploy these capabilities as a service, we need a new 6G infrastructure. An infrastructure where our vision is for 2030 that it will be completely cloud-based on a multi-cloud. Multi-cloud as in hyperscaler cloud, as in the cloud infrastructure of a communication service provider, as cloud compute capabilities inside an enterprise, or even at a radio station. And don't think cloud as only multi-core server blades, processor general purpose server blades, but think also more specialized accelerators like already exist for AI acceleration to do that in a more efficient way, graphical programming, but also acceleration of network functions, network processors, security, encryption engines and decryption engines, or also digital signal processing. And once you have such an infrastructure, you can benefit from all the goodies that cloud bring you. Cloud-native designs bring you, the flexibility, the ease of deployment, the introduction of new services. And so we see a future 6G communication and sensing infrastructure on top of that, with all the flexibility that cloud brings. And underneath that is what we call the essential adaptive network fabric. A high capacity, mostly optical network fabric with deterministic performance to interconnect these data centers, to connect also these edge clouds and far edge clouds with the base stations, either by passive optical networks or via wireless backhaul. And it is important to realize that this infrastructure is a network of networks, becoming actually fairly complex. There are the data center networks, there are different communication service provider networks, access networks, satellite networks, then there are enterprise networks, there are the endpoints of the networks will again be networks, a body area network, a machine area network, a car area network. So how do you create services in a flexible and frictionless way across all these networks? And so there's a whole research area then also in how do you leverage AI to automate that orchestration? How do you share in an efficient way the data and the AI models and in a secure way? So a whole area of research. And we've basically at Bell Labs structured our research along these three pillars: 6G communication and sensing networks, the essential fabric as a second pillar, and then the frictionless networking as the third pillar. So this is how we at Bell Labs core research bet on our research direction. Now, when we talk about 6G, we have 6 research vectors that we go after. 6G, there must be 6. So new spectrum technologies, of course. But then also using AI not only for automation of the network orchestration and operation, but also are there new ways of using it for the air interface? And then we expect ubiquitous radio around us. Can we use that not only as a connectivity means, but also as a sensor, helping us with that digital twinning of the physical worlds? Use it as a radar, use the Doppler effect to see breathing, heartbeats, or also machines, a rotating fan. What I'm seeing there is maybe a computer or a piece of equipment. So there's a lot of information that you can get out of radar signals, or also the way people walk. It's actually very individual, so you can even put identity to that. Then extreme network connectivity, extreme requirements for those body area networks, where it's mainly about energy, or a machine area network where it's mainly about reliability and extreme low latency. It can well be 100 microsecond latency and a nanosecond synchronicity. So very extreme requirements, very specialized. How do you support these in a future architecture? I already mentioned the cloud and multi-cloud architecture approach. And then last but not least, do this in a secure, privacy-conserving and trusted way. I won't go into each one of those. I'll lift out a few examples. So new spectrum technologies. These are the bands that we are using today. So mostly that low band, so you see the vertical axis, the frequency band. The horizontal axis shows for each of these frequencies what the reach is. And for 5G, we mostly use that mid-band, around 3.5 gigahertz. It's also the same band that we use for Wi-Fi, which allows us for connectivity still from existing cell sites. When 5G started, more than 10 years ago in research, there was a lot of hype and we go 5G millimeter wave is the thing. Lots of research invested. Actually, commercial deployment is still subscale. And why is that? Because of its limited reach, few hundred meters. So you need actually small cells, and that deployment is expensive. Putting every second lamppost a small cell is expensive. So it's not happening, and we can provide, back to solving a problem, but there is already a solution, you can actually provide high capacity also with the mid-band. So the question now is a lot of research excitement around terahertz, and maybe that is the thing now for 6G. A word of caution, millimeter wave is not yet happening. So why would you go to sub-terahertz? And maybe it is because there's another functionality than only the connectivity, because it provides you accurate sensing. By the way, we do invest a lot in the sub-terahertz because it does give us high capacity for backhaul. And so this is a bit our insurance. We invest for the backhaul, and if there is indeed that pivot to access, we are ready for it. But then there's another interesting band between just above the current mid-band, the 7 to 20 gigahertz, that we bet on. Because our simulations show that you can actually have coverage from existing cell sites. And if you can do it from existing cell sites, that's what you will do. And so I'll get into how we realize that. And the stepping stone is distributed MIMO and distributed massive MIMO. So we had, amongst others, with Sophie Paulin's interactions on creating massive MIMO systems. And distributed massive MIMO actually goes, so MIMO, first of all, for the non-radio people, is a large array, and you create beams with better signal-to-noise ratio, hence better capacity. And the interesting thing is you can have actually simultaneous beams, 8 up to 16 even, at the same time, increasing the capacity. Now, distributed MIMO means you have multiple such panels, and multiple panels listen to the same device. So intuitively, you see that you can increase even more the capacity. And we've demonstrated that in collaboration with AT&T. That's already 5G advanced. We see that as a stepping stone to 6G, to that 7 to 20 gigahertz, that new band still deployed from the existing cell sites. And the way we envisage that, you need many more antennas to get to that required signal-to-noise ratio and focus the energy to the devices. Now, it helps that the frequency is at least 2 times higher, so you have shorter wavelengths. In the same form factor, you can fit at least 4 times more antenna elements. But how do you architect this? What are the algorithms that you need, and to do this in an energy-efficient way? What are the processors behind this? And we actually have a collaboration also with Marianne Verhelst on efficient processor architectures to support that, and then also how do you create AI engines that help us, and I'll get to that part in a minute. But still, there is that sub-terahertz. And as I said, we are exploring technologies and working on these technologies for our wireless backhaul with an eye for mobile access and sensing applications. And there, an important challenge is how do you do this in a low-cost way with new materials? That today the packaging is often done with PCB materials. They're no longer amenable for these frequencies, and we have work on radio on glass and show that that is actually a much better material for low-cost packaging and interconnecting RFICs. And here a call out for collaborations with Patrick Reinarts. Patrick Reinarts here at the university, who was actually one of the first Bell Labs Prize winners for using such frequencies. And the interesting idea is it's not only free space, you can actually put these into a nylon plastic fiber and create high-speed connectivity in that way, in a low-cost way. But yeah, so I want to also call out for that. So you see that we actually have many interactions with you here at the faculty, and I'm very pleased with how fruitful these are. But then it's not only about new spectrum technologies, but I promised you to tell a little bit about how we use AI in a new way on the air interface. So this is the classical transmit-receiver with all the functional blocks, the synchronization, channel estimation, equalization, and all the way to the decoding and decoding. And already today, research looks at how can you use machine learning for optimizing these functions. And we're already, at every interface, you're losing information. If you combine these functions, can you get to even better performance? And can you maybe simplify? Because in your neural network, can you reduce the number of layers by combining them? So that you can already do in 5G. You don't need a new standard air interface. But if you have a new standard air interface with a feedback loop, you can actually have transmit and receive that just figure out how to communicate with each other by the virtue of machine learning and adapt to every new environment in a flexible way. And we've done first experiments that of two transmit-receive pair that actually figure out the modulation constellation in a dynamic way depending on the channel. And so the classical way to do this amplitude and phase, you have that QAM grid that you know very well. Here, the machine learning just figures out itself what the good constellation is and adapts to the channel changes. So we're going really after the Shannon limit. And so another iconic figure at Bell Labs. And so we're also having a fresh look at what does post-Shannon then look like. And the famous paper by Shannon on information theory had actually an interesting introduction by his colleague Weaver. And he described as actually 3 levels of communication. There is the transmission of bits and symbols with minimal error. And then there is a level of conveying the meaning, semantic communication. When I talk to you, do you understand what I'm saying? And then the third is, when I give an instruction at the other end, do you execute the goal as it is intended? And Shannon famously said, the second and the third, that is a human thing. The engineering problem is really bit transmission with minimum error. And for decades, we've used that as the focus for our research, going after the Shannon limit. But in an era where the endpoints are machines, we should have a fresh look at these level 2 and level 3. And I'll illustrate that with one example. At the endpoint, so here this is, the camera should identify, or the system should identify, the goal is to identify the people that are in the view of the camera. And so what do we do at the camera endpoint? You have a decoder that it extracts features, you send that over a network, and then at the other side, you have a coding system that compares with the database, goal, executed, identify the people. And today, the execution of identifying people and the transmission problem over the wireless network are separately treated. And especially if you are resource constrained in a wireless network or energy constrained, you likely go after a suboptimal solution. So why don't we combine the two and optimize across these two? And so this is really an example of goal-oriented communication. And so this is a new research area that we go after. There's also semantic communication. There's already dedicated seminars out there in the field. Last problem, just another example, is we want to go after 6G secure communication. And I want to introduce secure communication with quantum computing. A little bit to also show off that, like other industry labs, we do and invest in that long-term quantum computing. And why is this so important in the context of security? Well, there was a guy at Bell Labs, Peter Shor, that figured out when you have a quantum computer, the security codes that we deem safe today, and that you would need centuries with classical compute power to decode, well, with a quantum computer, you can actually decode that within hours. And quantum computers, it's probably still a decade out, depending on the roadmaps of different industry players. But you're already sending information today, and you can store that data, and in 10 years from now, that data, government data, or whatever it is, it can still be relevant. So quantum secure encryption is important. Another call out here for this university, the Nokia Bell Prize, which we award to an outstanding PhD. That Nokia Bell Prize last year went to Jan-Pieter Danvers from the group of Professor Bert Bruneel for a quantum-safe encryption scheme. A quantum-safe encryption scheme that was selected by the shortlisted by the American Standards Association NIST. So remains to be seen where that goes, but an important recognition for really world-class research that is happening here. Now, it's not only about quantum-safe computing and quantum-safe communication, and we're studying what that means for our systems, but then there's other things like how to deploy services on a zero-trust infrastructure, how do we preserve privacy, and how do we leverage AI/ML as a new tool to detect anomalies, but also as a new threat, a hacker that embeds functionality in a so-called trusted AI model, so you get a new cat and mouse game that we need to understand better. So I'm getting to the end. What you should take away is 6G. A driving direction for the application space is that digital physical fusion with the goal to unleash human productivity. The really defining technologies are AI and multi-cloud compute for the future of networking. And then last but very important, not least, very important, do this in a quantum safe and trusted way. And I actually forgot to say, but Happy New Year also. I forgot to mention that. Thank you.
Dankjewel Peter voor deze inspirerende lezing. Er zijn nog twee delen natuurlijk aan deze avond. Het is een officieel gedeelte en een minder officieel gedeelte. Ik veronderstel dat er nog wel wat vragen zijn in de zaal voor Peter of in verband met zijn lezing of andere vragen. Maar we hebben hier zo dadelijk nog een onofficieel gedeelte in de machinezaal waar er een natje en een droogje wordt aangeboden vanuit de faculteit en waar je nog even geduld moet hebben voor mijn nieuwjaarspeech te horen. Dus dat is voor straks. Maar het officiële gedeelte eerst is natuurlijk de aanstelling, de officiële aanstelling van u Peter als onze ereprofessor. En we hebben daarvoor een mooi doekje meegebracht met een foto van het kasteel. Het is jammer genoeg te slecht weer om de foto buiten te nemen. Vandaar dat we toch maar een foto meegenomen hebben van het kasteel om een mooie achtergrond te hebben. En als decaan van de faculteit Ingenieurswetenschappen heb ik de eer om u te benoemen als ereprofessor van deze faculteit. En wij hopen dat we de volgende jaren heel veel interactie mogen hebben met u. De connecties met de elektrotechniek zijn evident. Dat heeft u mooi geïllustreerd met verschillende voorbeelden. Maar ik hoop en ik denk dat dat ook wel vanzelfsprekend is, dat u ook als inspirerende figuur voor een hele hoop studenten nog kan fungeren in de loop van de volgende maanden en jaren. Dus hartelijk gefeliciteerd met uw aanstelling en ik hoop dat we elkaar nog veel kunnen ontmoeten in de toekomst. Proficiat. Proficiat. Voilà.